All right, welcome to another one of our online or video lessons. Now, the purpose of me doing these things isn't just because I like listening to myself speak. While some of you might think that's the case, I thought this would be a good way for anyone who wants to get ahead of the class. Okay, they can watch these videos before the actual lesson, and they can then use the lesson as a revision period, where I'll kind of give a shortened or truncated version of this longer, almost like a mini lecture is what I'm doing. That way, if you want to, you can go into a little bit more depth, or if you're just happy to kind of keep up with the class, you can just come to the lesson, listen, do the activities, and then use these videos as a potential like revision tool. However you like, I don't mind. We'll see how it goes, and if it doesn't end up working or it ends up being too much of Dr. Lathlane, then we can just stop it there. But anyway, so today we're going to be looking at energy transformations, particularly solar radiation. Forgot what we're talking about there. So particularly how does solar radiation kind of kickstart, or I guess influence, how energy is transferred or changed within the atmosphere and the ground and the earth and that sort of thing. Okay, so before we get into it, I thought it might be a good chance just to kind of look at where we are in the syllabus. So this is for the module Energy Transformations, which is the third module in Year 11, Earth and Environmental Sciences. Okay, and particularly looking at the inquiry question, how does energy drive Earth's processes? In particular, today's lesson is going to be all about analysing the role of solar radiation in driving Earth's processes, in particular radiation in relation to the water cycle. Now, I have crossed out the first part there, which is photosynthesis or living things. We'll get to that in another lesson, but I thought it might be just be helpful just to chunk it down into smaller bits, which might be more manageable. Okay, so this is what we're going to be talking about, looking at how solar radiation kind of interacts with water when it comes to the Earth, because we know that the Earth is largely made of water, and we'll see why that's important in a sec. And how that drives energy transformations. Okay, so without further ado, let's get started. Now, what better place to start than asking, well, what is solar energy? Solar radiation, sorry. Could be technically the same thing, but let's just keep with the term solar radiation. Well, firstly, we know that it comes from the sun. Okay, that's not surprising. Okay, so solar meaning sun, radiation usually referred to as heat or radiating out from an object. In this case, we refer to the heat or the wavelengths which come from the sun as part of the electromagnetic spectrum. Okay, and for those of you doing physics, you'll know that as the way we describe the different characteristics of some wavelengths or of light. They can be very small wavelengths which have lots of energy, or very long waves, more like radio waves, which have low energy. Now, in the case of the radiation that's hitting the Earth from the sun, it usually comes in three different forms or three different bands in the electromagnetic spectrum. And they include infrared, which is where a lot of the heat comes from, the visible light, that is all the colours that we see, and as well as the UV light or UV radiation, which we don't see but is potentially harmful to living things. We'll get to that in the next lesson. Now, I've just included this little diagram below here to show you whereabouts the visible spectrum sits in the overall electromagnetic spectrum. Somewhere in the middle. And so we really only see a small percentage of the entire electromagnetic spectrum. Sorry about that, if that hurt your ears. All right, still with me? Excellent. So that's what electromagnetic, that's what solar radiation is technically. It's a form of electromagnetic radiation, particularly within the infrared, visible and UV radiation. Now, if we were on another planet, potentially that a sun would emit different types of light. Therefore, the different lights reaching the Earth would be different. It wouldn't necessarily be in the visible light spectrum or the infrared. It could be a completely different part of that electromagnetic spectrum. But just so happens that in Earth, where we find ourselves, those are the frequencies which are being emitted by our sun. All right, so, sorry again. So imagine yourself, you're a little bit of a light beam, and you've just left the sun, and you're on a journey. Now you're heading straight towards Earth. What's going to happen to you? Well, you're traveling in space, there's nothing much happening there, because there's nothing really to run into, largely empty space, but all of a sudden you're approaching Earth's atmosphere. Let's think about all the different ways that you could react or behave, okay? Essentially, you as that little light beam can only react in one of three ways. Now, you can either reflect, okay? You can either reflect off something, and that will largely depend on the something that you hit and its properties. You could absorb or be completely subsumed by an object, okay? So then you just kind of get trapped. Or thirdly, you could neither reflect or get absorbed, you could kind of pass through it. And physicists refer to this passing through as refraction. So there are all the three different ways light or solar radiation can interact with the Earth. Not just the atmosphere, but the Earth as well and everything on it. Sorry. So, okay, so what's the chances, as you that little light beam, actually being reflected, being absorbed, or being refracted in that sense? Well, scientists, we like to understand these things. So we've actually gone along and measured all these sorts of different things that are happening in our atmosphere. And by and large, we can kind of come down to this sort of like percentage, or, you know, what happens to the light when it gets here. So in terms of reflection, we know that 6% immediately gets reflected back into outer space. Okay, so this is bounced straight off the outer atmosphere and just doesn't even go any further. Okay, so that's 6% of all light that comes from the light gets bounced off or reflected. Another 20%, it gets reflected or bounced off our clouds. Okay, so clouds are basically just water floating around in the sky, as we know. They bounce some light back out to space as well, so that's about 20%. And then finally, the oceans and the land themselves, the light that manages to get through, only 4% of that reaches the Earth gets bounced back and escapes into outer space, which is indicated by this that line there. All right, well, that's only 30% of describing of the whole 100% of light that comes through the atmosphere. What happens to the other 70, I wonder? Ooh. Well, let's have a look. All right, yes. There's a question there. What happens to the other remaining 70%? Okay, well, I'm glad you asked. So, 16% of that remaining 70% gets absorbed by the atmosphere, or somewhere like in the clouds, or in the water droplets, or vapor. Oh, so in the atmosphere itself, sorry, not the clouds. Then 3% of it gets absorbed by the clouds themselves. And then the majority of it though, so 51%, gets absorbed by the land and the oceans. Okay, so that's what's happening to them. Most of the light that's coming into our, or hitting the Earth, it's getting absorbed by the land and the oceans. Okay. Okay, well, another question, I'm glad you asked. What happens to this radiation after it's been absorbed? Okay, does it just sit there and do nothing? I'm pretty sure you know the answer is no. It actually either can re-emit itself, okay, or it can be transferred into other objects, okay, and then be passed on, or the energy that it holds can be passed on from object to object or area to area, okay? But again, we like to kind of be a bit more precise than that. So we know that 6% of that energy that was trapped in the Earth or the ocean gets radiated back out to space from the Earth, okay? And then 64%, so the other 64% of the 70%, eventually gets back to space from the clouds and the atmosphere, okay? So what you might be noticing here is that we have 100% coming in, okay, and eventually we have 100% going out. Now, that kind of balances out the equation, and it refers to, you know, the idea that, you know, matter is neither created nor destroyed, it just gets passed on or transferred into different sort of properties. But so too is the amount of solar radiation that's coming in. Eventually it all leaves and escapes. Now, it might take some of that light longer to escape than others, depending on what it gets absorbed into, but eventually it all will escape into outer space. Okay? So 30% of all that 100% that comes in will get escape into outer space because it's reflected. The other 70% will be radiated out either from the Earth or the clouds. Okay. Another way we like, the scientists, that is we, I'm talking about the royal we. But another way we like to think about the amount of light and different characteristics as it's coming through the atmosphere is thinking about how the different layers filter out or absorb different wavelengths. So what we have here is what's called a solar radiation spectrum. Okay, so that's looking at different heights, what happens to the frequency or the different types of wavelengths that are making it to the surface of, say, the stratosphere compared to the amount of frequencies or lights that's making it down to the Earth. Or even further, you could say what's making it down to 100 meters underneath the ocean's surface. And then this has implications for lots of different things, like what sort of organisms can live at depths of 100 meters, or, you know, what can exist on the land where it's reaching certain frequencies of light. Anyway, back to the graph. So if we kind of look at this carefully, we can see that there's different colors. So this this yellow represents the frequency of light. So we have wavelength down here on the x-axis and the frequency of those different wavelengths on the y. And we can see that the yellow represents how much of that wavelength or that light is present at the top of the atmosphere. Okay, that is before it's been filtered through the atmosphere, okay, and being, you know, sorted and bounced and reflected and that sort of thing. So you can see that the majority of it exists within the visible light spectrum. Okay, that's what's still within the most abundant type of light that's hitting the outer atmosphere. Then if we look at the red color, that's the amount of radiation now that we're seeing at sea level. Okay, so between the yellow and red, there's been some sort of filtration kind of, or absorption or reflection. So the frequencies of the different lights are going to vary. Now still, the most abundant type of light at the sea level would still be within the visible spectrum, but we still have a long skinny tail of infrared wavelengths to the right there. Now these blue sections here, they're called absorption bands. Okay, so these are the different types of wavelengths which get absorbed largely by clouds or H2O and CO2 or carbon dioxide in the atmosphere. Okay, so this is just showing how the differences in wavelengths of light changes as you go from the top of the atmosphere and you reach down to the bottom, the Earth's surface. All right, now before we go on, I thought it'd be good to kind of go through a couple of terms. Now, albedo, which is a term a lot of meteorologists use, as well as satellite mapping people, refers to the ratio between the amount of light an object absorbs compared to the amount of light it reflects. Now, depending on what object you are, or what your surface properties are like, whether you're smooth, reflective like a mirror, or let's say you're fluffy and dark like a black cat, okay? I know they're really weird examples, but those two objects are going to absorb and reflect light differently, okay? And they're going to have a specific albedo. Not libido, by the way. Sounds similar, but completely different. Albedo, okay? Now, in this, albedo number is referred to as a decimal, okay? Usually ranging between 0 and 1, Okay, 1 meaning it has high reflectivity. Okay, it doesn't absorb a lot, and closer to 0 means it has a high absorption, low reflectivity. Okay, so when we're talking about albedo, we're really talking about just about this small little interaction here, where we have the sunlight hitting an object on the Earth's surface, whether that be water, a rock, tree, an animal, or whatever it is, and we're understanding how much of that gets re-emitted back into outer space. All right, so we can see here that just taking a brief look at some of the most common things that you would expect light to reflect or absorb from, we can see that ocean, it has a very low albedo. It has 0.06. Okay, so that means that it absorbs most of its most of the light that comes in contact with it. Okay, you might think that's a bit strange because when you're looking at the light reflecting off the ocean, it can usually be quite bright. However, it's only a small percentage of the amount of light that is actually hitting the ocean in the first place. Then, if we go to looking at rainforests, now rainforests are usually very heterogeneous in terms of their surface is very, I guess, varied. So there's going to be lots of reflection, refraction, things kind of bouncing off everywhere. So therefore it has a higher ability, a higher chance to absorb as well as reflect light. And that's why it has a range between, depending on type of rainforest, between 0.8 and 0.18. Okay, so going from more absorption to less absorption. And if we think of grass, it looks very nice. It again absorbs less and emits more reflective light. And of course, if you think of what it's like at the snow, on a very sunny day, most of the light will be reflected off the surface of snow. Okay. Now you might be thinking, that's great. I don't really need to know this sort of stuff. Well, in fact, we can actually use this very cleverly to make very important maps, especially for meteorologists as well as Earth environmental scientists who are monitoring changes in vegetation over time. So for example, this satellite image of chlorophyll A concentration shows the amount of chlorophyll in the ocean off the east coast of the United States. And not only can it show you where what's called all these oceanographic currents are moving through time, it can also tell you where they're most likely to find the most nutrients, because chlorophyll is a form of nutrients in the ocean, as well as the map on the right there, that's showing you the vegetation structure, basically based on the amount of light that's reflected off the different properties of the ground, and we can map like the decline of the Amazon rainforest quite precisely. So if any of you are interested, this is a really up-and-coming sort of area of science research which there's a high demand for, and it's really applicable, and you can do lots of great stuff just from the comfy chair in your office. You can just get access to all the satellite information. All right, now moving back specifically to this relationship between solar radiation and the movements of energy and water in the Earth's atmosphere, in the oceans particularly, we need to consider some other things about what's unique about Earth. So we know, hopefully, you know, that the Earth is tilted, okay? On an axis, I believe it's 23.5 degrees, so it's quite substantial. And that technically gives us our seasons, okay? As well as the fact that the Earth is revolving around the Sun in an elliptical orbit, so it's not completely circular, okay? So sometimes the Earth will get closer to the Sun, and sometimes it'll be further away, and these help regulate the seasons as well as its tilt. Another important thing we need to understand about solar radiation and the Earth and the amount of energy that's hitting the surface is that because of the curved structure of the Earth, there's more intense solar radiation at the equators than there is towards the poles. Now the reason for this is that if you kind of imagine the same amount of light is being concentrated on a smaller area of the Earth's surface at the equator, whereas if you move towards the poles, that same amount of light is being spread out over a larger surface area. And this is generally why it's colder towards the poles than it is at the tropics, okay? Because there's less concentration of solar radiation. Now what we can see over here is that process in action, okay, on any particular day. If we were just looking at, I believe that's the amount of solar radiation hitting the Earth's surface. Obviously there's some clouds and things happening in there, but you can generally see that this is during the austral summer, that is the southern summer, because large areas of the northern hemisphere are still in darkness and are not receiving any solar radiation, whereas the Antarctica down here is receiving some solar radiation. So this is probably in the height of summer in a particular day, who knows. So if we take the average of every single day over numerous years, we end up having a graph which sort of looks like this. Okay, well, not sort of, exactly looks like this. So this shows us the average amount of solar radiation spread across the entire globe, average for decades. And what we can see here is that within the equator or the low latitude areas, we have high amounts of solar radiation, indicated here by the warm orange and red colors. And as we head towards the poles, we see this latitudinal gradient, that is, with increasing latitude, we see a decrease in solar radiation. And that kind of just reflects, again, this idea that the same amount of light is being spread across a larger area as you head towards the poles. Okay, so that's some of the, I guess, key physical relationships between, I guess, how the solar radiation enters and impacts the Earth's surface. Now we're going to just really hone in on how this solar radiation from the sun really impacts the water cycle or the hydrosphere, that is, any part of the water cycle at the surface of the planet, okay, or even within the lithosphere or the rock. Now, it probably comes as no surprise to you that the Earth is a very blue planet. Now, Carl Sagan, I'm not sure if you know who he was, but when the first Voyager satellite was sent past like the moon out to past our solar system, and it turned back and looked at Earth, he looked back and it saw a little blue dot just floating in space, and that blue dot is largely because we are a blue planet. Alright, well, I'll stop being all philosophical because it wasn't very impressive anyway, but basically where 71% of the Earth's surface is covered by water. That's not just the oceans, but also like rivers, lakes, and those sorts of things. Now, we will go in a moment breaking through, well, where is all that water found and what sort of characteristics does that water have, because that's important. But just by and large, know that 71% of the Earth's surface is water, and 97% of this water is in near the surface. Okay, meaning it's within the first 100 meters or so of the Earth's surface, so not a lot of it is actually down underground. So if we were to look about where all this water is found on Earth, okay, we'd first find that most of it, unsurprisingly, is in the oceans. Okay, 97.2%. The next big player in terms of where the ocean is stored is the ice caps or glaciers. Okay, so they store about 2.15% of the Earth's waters. Might not seem like a lot, but if you imagine all that ice, and if it were to melt because of climate change, it would very much have a devastating effect on sea levels, because it still is 2.15%, it's still a lot of water. Okay, and then the next most abundant area where water is found is in the ground, which represents just 3.1%. Okay, you can see where I'm going with this, I'm getting lower and lower. Then, if we think about all the lakes in the world, okay, these standing bodies of water, not connected to any rivers or oceans, these lakes, they represent 0.009% of the Earth's water. Okay? Now, we haven't mentioned a couple of things. I wonder what you're thinking was going to come next. If you're thinking atmosphere, then you thought right. Interestingly, even though we look at all the clouds and all the water vapor that's going out into the atmosphere, it only represents 0.001% of all the water that's on our planet. Similarly, we have rivers, which is our, I guess, the smallest amount, coming in at 0.0001% of all the water is found in freshwater rivers. Now if you were to do your maths and add all that, you're still not quite getting to 100%, and that's because a lot of water, well, not a lot, but some of the water is in living things like us. Again, not a lot, but in a sense, we kind of think water is vital to life, and it is, but really, we don't need a lot of it. Okay, so that's just kind of where water is found across the globe. Now, in terms of water, what's so special about water? Well, we could go on for a whole hour or so about different chemical and physical properties of water. I won't bore you with that, though some of you chemists out there might like to know about that, so you can go do your own research. But some of the great things about water and why we're so lucky to have a lot of it is because here on planet Earth, it exists in its all three states. And that's largely due because of the distance that the planet Earth is from the sun, and the pressure in the atmosphere and all those sorts of things, okay, and like gravity. So lots of things gone into concocting this sort of miracle. However, those three states are liquid water, solid water, and gas. So, you might not think this is particularly special, but not a lot of other planets are lucky enough to have water in all these three different states. And it's important because these three states can only exist when the pressure, temperature are just right. So they have to stay within a narrow band. Another really great thing about water is that it acts as a universal solvent. Okay, that means that it dissolves pretty much everything. And that's really important if you want to transport things, especially in living organisms. Sorry, my nose is just a bit itchy. But yeah, so that's really important in terms of its properties of water. Can dissolve most salts. As well as an important kind of characteristic of water is, as you know, when it freezes, unlike other physical properties, when they go below their freezing point, they contract. Whereas because of the hydrogen bonding in water molecules, they actually expand. And this makes frozen water less dense than liquid water. And what does that mean? Well, that means that ice floats. And this can be quite important, especially for many living things, like polar bears, for example, who rely on this physical property of water for their habitat. Okay? And fourthly, the next most important property of water, and why we're lucky to have it, is that it has a high specific heat characteristic. And what I mean by this, it can absorb a lot of heat, okay, and it doesn't lose it easily like some other physical chemicals or physical properties. They're not very good at retaining the heat. They can quickly heat up and they can quickly cool down, but not water. Water is great in this sense that it takes a lot of energy for it to heat up a degree, but also it takes a long time for it to cool down. So in this sense, it keeps whatever environment that water is found in, keeps it quite stable. And this is great for living things because we're all about stability. We don't want to be fluctuating all the time. Now that we've thought about where water is, how it behaves, we are ready to think about the water cycle and what that is and how it's driven by solar radiation. So really, the water cycle, if you haven't already figured it out, is just this scientific model for trying to describe the movement of water around the globe, okay? And I'm sure you probably remember this from primary school and things, and you would have learned about evaporation, transpiration and rain, precipitation, all those sorts of things. And in a way, some of this might not come as a surprise or shock to you, but we're going to go into a little bit more depth about these key terms and what they actually mean when we're talking about it in science, because before we can understand how energy is involved in this process, we need to understand some of the terms. So we need to understand firstly, why is the water cycle important? Well, it's important because, well, it keeps things cycling, surprise, surprise, but also it moves matter and it moves energy, either that by actually picking things up like sediment or nutrients and moving them downriver, or just by passing on energy through latent heat. Okay, and I'll talk a bit more about what I mean by that in a second. So this all comes back to the amount of sunlight which is actually hitting the Earth's surface. Because if we think about what's happening at a molecular or particle level, when the sunlight hits the water, it starts exciting. It starts exciting those molecules, and they start vibrating more. And if they're vibrating more, they're more likely to go through what's called a phase shift. That is basically just a fancy word for saying they go from a solid to a liquid, or a liquid to a gas. Okay, and this is how the whole water cycle is kicked off or generated. It's from the solar energy that's hitting the land. So, first term we're going to talk about, evaporation. Okay, we've all come across this before, and it's this process of converting liquid water into a gas. Okay, and likewise, like I was just saying before about the excitability of the molecules, it all relates to how much temperature is within a system, okay, and that temperature is directly related to solar energy in most cases. Okay, not always, but in most cases it is. That's why in the morning you'll start seeing this nice mist coming off a lot of the damp logs and even the roads and things like that, because the sun's starting to increase the amount of evaporation. Fun fact, I didn't know this, but 17 million litres of water evaporates into the atmosphere every single second, okay? So that makes evaporation a very important process in the water cycle. All right, so on the other end of the spectrum, so if you think about evaporation, what goes up must come down. And here we're talking about precipitation. Now, a lot of the time we think of precipitation just rain, okay, but it's much more than that. It's also about falling ice and snow, okay? Those two things can also be classified as precipitation, okay? And it's basically the process of water that's trapped in the atmosphere falling down to the Earth's surface, okay? Now, while you might think this is all fairly straightforward, yes, rain, comes from the sky, there's an important little thing we need to understand what's going on when the cloud starts to form droplets. Now that water molecule is carrying energy, albeit potential energy, up and up and up and up. And as it starts to cool down, that potential energy is converted into gravitational energy, okay, as it starts to fall. And as the rain droplet's falling, if it runs into something, or it hits something when it hits the ground, it will convert that gravitational energy into kinetic energy. And that kinetic energy can have massive effects over long periods of time. And we just have to think about what we were learning in our previous modules about the rock cycle and erosion and weathering. That's all to do with the amount of energy that rain droplets convert when they start to condense and fall to the ground. Okay, so this process is very important, and we need to understand it's this idea of energy being converted as it condenses into a different state. Okay, and I guess another key term of aspect of the water cycle is the runoff. Again, similar to erosion, that sort of thing. It's moving matter or products around the Earth's surface. And then also percolation. So this is the process where water starts to seep down into the Earth's groundwater, and becomes groundwater. Okay. Now, you might have heard of this word, transpiration. This is when plants, it's a physical process, when plants basically, they kind of sweat, okay? Just like we sweat, plants sweat as well, okay? out of their glands called stomata. Now, this also is a form of evaporation, okay, and it contributes to the clouds as well. So you might know that the Amazon or the Congolese rainforest, they produce their own climate because of this process of transpiration. They produce their own clouds, which is quite fascinating. And sometimes when we're thinking about this process of transpiration and evaporation, we use the term evapotranspiration. I know, it sounds pretty cool. Now, this is all well and good. Transpiration, precipitation, what was that for? Evaporation, all those sorts of things. They're all great, all parts of the water cycle. Now, there's one thing that you might not be familiar with. We spoke about convection, which is the transfer of matter, energy, or materials through different densities. Okay, so moving up or down, usually in a vertical process. Advection is similar in the sense, instead of going up and down, and because of differences in densities, it's moving material through fluids in horizontal fashion. So for example, here, where we're looking at the movement of wind or air particles across the land, which could be quite warm, and as soon as they hit the water, which is quite cold, that hot air then condenses to form fog. That is a process. Process that results from advection. Sorry. All right. So if we think of the two terms, advection and convection. Advection, if we're thinking of like a atmospheric convection cell, the advection process is the horizontal movement of the cell as it's moving either along the surface of the Earth or along the upper atmosphere. Okay, so advection is this horizontal movement, whereas convection is this process of moving up and down due to differences in densities. Okay, now advection is very important for understanding weather. Okay, so if you're wanting to be a meteorologist, not a metallurgist, sorry, it's completely different. A meteorologist, you really need to understand what advection is and how it works. Okay, because basically it's just wind. Okay, and it can cause cyclones and all the different devastating effects that causes, as well as it can be responsible for massive amounts of waves, which have large amounts of energy, of course. Now, it's interestingly, this advection process has so much energy and it drives most of the atmospheric conditions that we see today. Yeah, we're only starting to really tap into that as a renewable resource, like in terms of wind farming and hydroelectricity. So again, just kind of referring to this idea of atmospheric convection. Okay, so similar to our oceanographic convection, where the warmer particles, or the warmer things, or the cooler, sorry, I should start with the cooler molecules are more dense, so they sink to the bottom of the ocean, starting this oceanographic conveyor belt. Likewise, in the atmosphere, when we have more intense solar radiation happening at the equator, so here on the left, it's going to increase the temperature and therefore increase the amount of particle activity, and that's going to cause those air particles or water vapor to rise. Okay, then as it gets higher up into the atmosphere, it's going to cool down, and where it will eventually sink and move towards the higher latitudes of the poles. Okay, so this is a kind of a general schematic diagram of what happens in the atmosphere in terms of heating and cooling. So generally, like I said, it's hotter at the equator, so that causes air at the surface to rise, and as it rises, it moves further towards the poles as it starts to cool, and we have these really large convection cells which are operating from all the way from the equator region all the way down to the poles. Now, we'll talk about this more in detail in a couple of lessons time, but just be aware that you have this sort of convection cell that kind of covers the whole globe, and sometimes we can see smaller ones within there, but at this point in time I just want you to see that at the equator, hot air rises and it pushes the colder air towards the poles, where it starts to descend because it's heavier. Alright, so we're nearly at the end. We're out at the end of our little lesson. So before I go, I just thought it might be good to go through some take-home messages about today. So the first thing is that variations in heating and cooling lead to water movement. Okay, basically it's the driver of the water cycle. The Earth, we're quite unusual in the fact that we have water in its various different states, all simultaneously in some cases. And thirdly, the gain or loss of energy causes water to change state and to move. Okay, so this relationship between movement and energy, they're all interconnected. Okay. Now, for our next lesson, if you're interested, we're going to be looking at how solar radiation affects the biosphere, or in particular living things. Okay, and I just have a couple of pictures there which refer to all the different organisms that rely heavily on light for photosynthesis. Alright, so I'm hoping that you're still listening and you've got through my coughs. I'm sorry about that. But yeah, and I'll see you in class. Excellent, bye.